So in this section, we discuss the so-called bounded linear operators. First, let us recall the definition of a linear operator. Given two vector spaces x and y over the field K. So K is either the field of real numbers or the field of complex numbers. We say that a map T from x to y, a linear operator, if the following equations or equation is satisfied. So T of x plus alpha y is equal to T of x plus alpha T of y. For any pair of vectors x and y in capital X, and for any scalar alpha in the field K. You should take note that here on the left-hand side, the scalar multiplication and the addition should be taken with respect to the vector space X, while on the right-hand side, the scalar multiplication and the vector addition should be taken with respect to the vector space Y. So in particular, if T is linear, so here we abbreviate sometimes a linear operator by just saying that it is linear. So if T is linear, then the image of the zero vector in X is the zero vector in Y. So one must not be confused with this notation, since we are denoting the same notation for the zero vectors in X and Y. So the notation should be taken with respect to the appropriate context. So here, since 0 is taken as an argument of T, should be an element of the domain. That is the vector space X. So if you take the image, the zero vector on the right must be the zero vector on the vector space Y. Well, this follows immediately if you take, let's say, X and Y to be the zero vector in X and alpha to be 1. So linearity implies that. Okay, so let's start with the left-hand side. That would be T0 plus 0 or 1 times 0. Of course, this is just the zero vector. Linearity implies that this is T of 0 plus 1 times T of 0. And immediately you can see by canceling T of 0. And since 1 times T of 0 is T of 0, you get this equality here. So for linear operators, the image of the zero vector in the domain is the zero vector in the codomain. So as an example, a map T from R to R is linear if and only if there exists an M, a real number M, such that Tx is equal to Mx for all x in R. Okay, so a linear function must be of this form, mx plus b. But this is not a linear operator unless b is not equal to 0. You can see that based on this equation. So if you replace x by 0, in order for this to be satisfied, B must be 0. Okay, so a linear operator must pass through the origin. So in this case, linear operators from R into itself are functions having this form. So M, some real number M times the argument X. Okay, and we will give further examples later. Now, let us add additional structure on our vector spaces. Suppose now that X and Y are norm spaces. Then a linear operator, say T, from X into Y. This is said to be bounded if we can find a constant M that is non-negative such that the map or the image of T of X the norm of that with respect to Y is majorized by the constant M times the norm of X with respect to the vector space or norm space capital X. So for linear operators, we will, let's say, follow the notation without the parentheses. So T of X is the image of X under T. So here we ignore the parentheses to mimic the action of matrices in the case of finite dimensional linear operators. Okay. So in particular, linear operators maps bounded sets in X into bounded sets in Y according to this inequality. Well, for linear operators, the following are equivalent. So let us state that as a theorem. So suppose I have a linear operator and X and Y are norm spaces. So the following items are equivalent. First, boundedness of T is equivalent to the fact that T is Lipschitz continuous. These two are also equivalent to the continuity of your linear operator. And finally, these three are equivalent to the continuity of your operator at the origin. So again, for linear operators between norm spaces, boundedness, Lipschitz continuity, continuity, and continuity at 0 are all equivalent. So let us look at the proof of this theorem. So let's start or we show the following implications. 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. In fact, the last is the one that is not so trivial. Okay, 1 implies 2, that would follow immediately from linearity and boundedness, since you will get the following. So t of x minus t of y, so the norm is taken with respect to y, is equal to, by linearity, t of x minus y, but this is less than or equal to m by, according to boundedness, m times the norm of x minus y. And this is precisely Lipschitz continuity. Of course, a Lipschitz continuous function is continuous. This is trivial. And similarly, a continuous function is continuous at every point in the domain. So therefore, it is also continuous at the particular point 0. That is, again, a trivial. Now, to prove the last implication, okay, so let us suppose here that t is continuous at a 0. Okay, so here, applying the definition of continuity, and we take, let's say, the epsilon value to be 1. So there is a delta, positive, such that the norm, if the norm of x minus 0, so that's basically the norm of x. If the norm of x is less than delta, then the norm of t of x minus t of 0, but this one is also equal to 0, so we can ignore that. The norm is less than epsilon, and as I said, we take epsilon to be 1. So this is merely applying the definition of continuity at a point and taking a particular value of epsilon. Now, given, let's say, an x that is not 0, let us define y to be, let's say, x, or eta x divided by the norm of x. So the denominator here is not equal to 0 due to the assumption on x. Here, eta is some number less than delta. Okay, then if we calculate, let's say, the norm of y, you can see that this is, you apply homogeneity. This is equal to eta, but since eta is less than delta, hence we know that the norm of t of y, according to this property, is less than 1. So plugging the definition of y, so this is t of eta x divided by the norm of x, and then take the norm with respect to y. Applying linearity and the homogeneity of the norm, we can pull out these two constants outside t and then outside the norm in order to obtain the following. So this is eta divided by the norm of x times t of x. So this implies that T of x, the norm T of x in y. Okay, so as I said, we now remove the parentheses. Okay, so let us write this as Tx and Tx. And same here. So dividing by eta over the norm of x, we will have 1 over eta times the norm of x. And this is true for any x not equal to 0. If we, let's say, include 0 here, then we need to put the equality because both sides would be equal to 0. Okay, so now you can choose m to be the reciprocal of eta. And this implies that T is bounded. And that completes the proof of the equivalence. Again, for linear operators, boundedness, Lipschitz continuity, continuity, and continuity at 0 are all equivalent. So for instance, if you want to prove that your linear operator is continuous, it is enough to prove that it is bounded. So let us denote by Lx comma y to be the set of all linear operators from x to y. And they are bounded. Equivalently, L of xy is the set of all bounded or set of all linear and continuous operators from x into y. And this is, of course, a vector space. Okay, taken as a subspace of functions from x into y. And for this vector space, we equip it with the norm. So for a bounded linear operator, say T, in Lxy, we take the least upper bound, m, in the definition. So this is the infimum over all bounds m in such a way that this inequality, that is the norm of the image, is majorized by the constant or the bound m times the norm of x for any x in capital X. So here we are already claiming that this is a norm. In fact, you can prove this immediately using the definitions or the properties of a norm. And I will leave the details for you to verify. Well, there's an alternative and more convenient way of characterizing the norm of a bounded linear operator. The norm of a bounded linear operator is also the largest norm of images of the, let's say, unit sphere in the vector space. You can replace this unit sphere by the unit ball as well. And by, let's say, normalization, you can replace this by any vector in X as long as it is non-zero. Okay, so to prove this, let us denote, let's say, this as N1, N2, and say this is N3. And let's say this is the norm. Okay. So for this, applying, let's say, homogeneity, we have the following. So if X is in capital X, take note that the norm of X so suppose that also the norm is equal to 1. Okay, then the norm of T of X is less than, of course, or equal to N1. Since N1 is the supremum of the norm of images having a norm of argument equal to 1. And I can write, of course, this by, I can multiply by 1. Okay. So N1 is a bound for is a bound for the operator T. Therefore, by the definition of the norm, it is, since it is the infimum, so the infimum is smaller than N1. So this implies that the norm of T is less than or equal to N1. Likewise, if you note or you observe that the unit sphere in X is a subset of the closed unit ball in X. And from this, the supremum of the unit ball, closed unit ball, must be larger or equal to the supremum over the unit sphere. So here we have N1 less than or equal to N2. Okay. Now to prove the next inequality. So if X is in a capital X and let's say it is non-zero, and the norm is less than or equal to 1, let's say, then we know that T of X, the norm of T of X divided by the norm of X is less than or equal to N3. Since N3 is the supremum here. Okay, so with this, let us multiply both sides by the norm of X. Hence, from this, take note that this is also valid for x equals 0, because both sides would be 0. Okay, so we can now include here the equality for 0. And since the norm is non-negative, we can ignore that one. Okay. So if I take, let's say, the supremum over all x in the closed unit ball, this implies that. So the supremum of the left-hand side would be n2. The supremum of the left-hand side would be n3 because this is bounded by 1. Okay. Now our next goal, in order to show that these quantities are all equal, we only need to show that n3 is less than or equal to the norm of x. Okay, so for this matter, let us take positive, or let's say a non-negative m be such that m is an upper bound for t. In other words, this inequality is satisfied. So for x not equal to 0, we can define or divide by the norm of x. And if we take taking the supremum, you end up with, okay, by the definition of n3, this is n3 less than or equal to m. Okay, so this is not yet the final conclusion, of course. We still need to take, since m is an arbitrary bound, we need to take the infimum over all m. So this should be n3. And the infimum over all m that satisfies this inequality is, according to the definition, the norm of your bounded linear operator T. Okay, so this is less than or equal to this, and in turn, this is less than or equal to that, which is also less than or equal to this, and also this is less than or equal to that. Hence, all inequalities must be equalities. Okay. So according to this, you can alternatively prove that this is a norm by showing any of these to be norms in the space of linear and bounded operators. So for instance, you can use this, okay, to show that to show the triangle inequality, the homogeneity and the positivity of your norm. Okay, so that's an alternative way in establishing that this is indeed a norm on LXY. So based on this inequality, if I take the infimum over all m, we have the following estimate. So for every t that is linear and bounded from x into y, the norm of the image is less than or equal to the norm of the operator times the norm of the pre-image. Also, one can show the following. So if suppose now we have three norm spaces, X, Y, and Z. And T is a bounded linear operator from X into Y. And S is a bounded linear operator from Y to Z. Then the composition ST, which we use without the notation for the composition. So think of this, for instance, as an analogy, the product of matrices. Then the composition is bounded from X to Z. And furthermore, one can estimate the norm of the composition by the product of the norms. X, Y. Well, to see this, we can use N3 as an alternative definition for the norm. So for any, or let's say we can use N2, okay. And okay, so for any X in the closed unit ball of capital X, we have the following. Okay, so according to this property, okay, so this is less than or equal to the norm of S times the norm of the argument. In this case, this is Tx. And applying the same inequality once more, the second term is less than or equal to the norm of T in Lxy times the norm of X. Since the norm of X is less than 1, you end up with the following product. And then you take the supremum again. Overall elements of the closed unit ball in X. So the supremum of this overall X satisfying this condition would be this left-hand side. Okay. So that's somewhat a sub-multiplicativity of the norm with respect to function composition. The following is a special type of bounded linear operators. So let's say if Y is a norm space, X is a finite dimensional norm space, and T is linear, then T is bounded. So in other words, linear operator defined on a finite dimensional norm space is necessarily bounded. So let us look at the proof. Let us start with a basis of x. Okay, then any given x in your finite dimensional norm space, there exists, let's say, x sub i's, so x1 up to xn in the field, such that x can be written as a linear combination of your basis vectors. Okay. So there's a one-to-one correspondence. Let's denote that by, let's say, J from K to the N. So an X, Jx, in fact, this N tuple here is unique, okay, since you have a basis. So this map is well defined. And we know that this is bijective. And we have seen this in the previous lectures. In fact, injectivity follows from the fact that your basis is linearly independent, and it is surjective because it spans the whole vector space. In this way, the map defined from, let's say, X into R, defined as follows. So you just take, let's say, the sum of the coefficients with respect to the basis. This map is a norm on X. Take note that this is the same as what the little L1 norm of your image. So from this, you can simply apply the linearity of J and the fact that you have the L1, little L1 norm to show that this is indeed a norm. Of course, for positive definiteness, you need the fact that J is bijective. So from this, we can now say that thus there is a constant C greater than 0 such that the this particular norm, okay, is less than or equal to the constant C times the given norm of your finite dimensional space. So here we are using the fact that all norms on a finite dimensional vector space are equivalent, and we only take the one inequality. And we now have all the ingredients in proving the boundedness of your linear operator. So first, you apply linearity and the definition of X according to this equality here. This would be X sub K T E K. And then by the triangle inequality, this is less than or equal to. So the norm of the sum or the norm of a linear combination is less than the linear combination of the norms. However, you need to take the absolute value of the coefficients. If we set, let's say, if you calculate the maximum, so let us take the max of this, k from 1 to n. So taking the max, you obtain this inequality, which is, by definition, this norm of x, according to this one. And this is now less than or equal to some constant m times the norm of x, where m is equal to the max of the norms of the basis, the images of the basis vectors, times c, where c is the constant from this inequality. So you can estimate this by c times the norm of x. That's why we have a constant c here. And according to the definition, therefore, since take note that x is an arbitrary element, this implies that t is bounded. So all linear operators defined on a finite dimensional space is necessarily bounded. In particular, let's say if I have a given matrix A, and let's say n by m, let us define an operator T sub A from Rm into Rn by the following. So Ta of x is A times x for any x in Rm. So you can check that indeed the dimensions here are correct. So this is clearly a linear. So T sub A is nothing but the action of your matrix A. Since our domain is finite dimensional, according to the previous theorem, T sub A must be a bounded linear operator from, I should replace this by K. It's a bounded linear operator from Kn into Kn. In fact, there's a one-to-one, this is a one-to-one correspondence between linear operators from Kn into Kn and the set of n by n matrices. So there's a natural one-to-one correspondence. So based on this example, you can think of matrices as a specific type of bounded linear operators. Further examples, we have, let's say, an integral operator. So define, say, t space of from the space of continuous functions on the closed interval 0, 1 to the space of continuously differentiable functions on the same interval. So given a continuous function f, so this must be again a function, and what is the action? So here you just take the integral from 0 to x of f. Of course, x here is in the closed interval. Then one can show that t is in fact a linear operator since the integral is linear, and it is also bounded. Having a norm the norm is equal to 1. Okay. So it lies on the unit sphere of the space of bounded linear operators from between these spaces. Okay. So in particular, T is an isometry. So the fact that it has a norm 1, it is left for you to verify. So you can check it as an exercise. As a final example, we consider differential operators. So suppose omega is in Rn, and this is measurable. Lebesgue measurable, to be precise. And let us take a positive integer m. And let us consider some family of functions C sub alpha defined from omega to R. So these are real valued. For all multi-indices alpha. So here you include a zero entry. You may include a zero entry. So for any multi-indices alpha of length at most m, so that is basically the sum of the components. And let us formally define the operator Tf to be the following linear differential operator having coefficient C sub alpha. So here, the derivative can be, let's say, the strong derivative or your weak derivatives. So depending on the properties of your coefficients, we have the following. So first, if let's say, if omega is, let's say, open and bounded, and C alpha is continuous for any multi-index alpha but most m, then T would be a bounded linear operator in Cm, that's the highest degree, into C bar. Of course, it is clear that T is linear. For boundedness, you apply the definition of the norms in CM and C, and you will recognize that indeed T is bounded. Again, if omega is open and bounded, and C alpha belong to the Holder space C0 beta, for every alpha, okay, for some beta positive but less than or equal to 1, then you can check that T is a bounded linear operator between the Holder spaces Cm beta and C0 beta. Now, for coefficients C alpha that belong to Lebesgue spaces, we have the following. So for this, it is enough to consider that omega is measurable. We have, let's say, 3 exponents, P, Q, and R, wherein the sum of the reciprocals of P and Q is equal to the reciprocal of R. And now your coefficients belong to LQ. For every alpha with length at most m. Then T is a bounded linear operator between the Sobolev space WMP and LR. And you can establish this by Holder's inequality, for instance. So the details of this example is again left for you to verify. So depending on the regularity of your coefficients, your linear operator will be bounded on appropriate function spaces. So here we have the space of continuously differentiable functions, the Holder functions, and then the Sobolev functions as well. Now, if Y is a Banach space, then the set of linear operators equipped with the operator norm is also a Banach space. So for the space of bounded and linear operators between two norm spaces, in order for that to be a Banach space or to be complete, it is enough to take the completeness or to assume the completeness of the codomain or the target space Y. Okay, and the proof is, let's say, similar to the proof of the completeness of the space of continuous functions from X to Y. Okay, and let us review the proof for completeness. So let's start with a Cauchy sequence and LXY. Okay. So this means that the norm of, let's say, T sub K minus T sub L of X. So given a positive epsilon, there exists, let's say, a constant n or a natural number n, such that this is less than epsilon over 2 for any sufficiently large indices k and l. That is, k and l greater or equal to n. Now, we apply, going back to this inequality here. So applying this inequality and the linearity of your operators, we end up with the following estimate. So now the norm of the image of the difference is less than epsilon over 2 times the norm of x. So this is now true for any KL greater than or equal to n, and for any x in your domain. This estimate implies that, of course, given a particular x, the set of images is Cauchy in Y for each x in your domain. Thus, there exists a map T from x into Y such that T of x, so you take the limit of the images. And take note that this is unique due to the fact that your space Y is a Banach space. So the limit exists and it is unique. So therefore, one can introduce a map. And this is linear. So, well, you can verify this immediately by applying the linearity of the operators T sub K and applying the linearity of limits and the uniqueness of limits. So this is now linear. Okay. To prove boundedness and convergence, we can start with this. You take the limit as L goes to infinity. So that would be dx. And this should be now less than or equal to epsilon over 2 times the norm of x. This implies that this is a bound for the difference. So the norm of tk minus t is less than or equal to epsilon over 2, and this is now less than epsilon. And from this, take note that this is true for any k greater than or equal to n. And from this inequality, according to the definition of the limit, this implies that T sub k converges to T, in the space of bounded linear operators. And of course, T is bounded. And the boundedness follows immediately from the fact that T sub k is bounded, and you apply here the reverse triangle inequality. So the chosen Cauchy sequence converge to an element in LXY. Since this is an arbitrary Cauchy sequence in your space of bounded linear operators, therefore, that vector space is a Banach space when equipped with the operator norm.